And now I can turn it around and have a look at the writing that's been hiding underneath.
So no one's seen that writing for 4,000 or 5,000 years?
Yeah, the only person that's seen it previously is the one who wrote it.
For over a century, a mysterious clay tablet sat ignored in a museum drawer, dismissed as nothing more than an ancient record.
The scholars who have specialized in studying Babylonian mathematics have never been able to come to an agreement about what it was for.
But when AI was finally used to decode its markings, researchers were stunned. Hidden in its faded symbols was a discovery so advanced it shattered everything we thought we knew about the origins of mathematics. Buried in sand, forgotten by time, over 100 years ago, in the ruins of ancient Mesopotamia, a group of archaeologists worked tirelessly under the blazing sun. They were searching near what is now southern Iraq, a region once home to one of the world's earliest and most advanced civilizations. The ground was littered with fragments of pottery, toppled statues, and countless clay tablets. These tablets were often filled with carvings of gods, stories of kings, or detailed records of religious rituals and trade. Such pieces were highly valued because they gave historians clear insight into the beliefs, rulers, and daily life of the ancient world. Amid these remarkable discoveries, there was one object that seemed completely unimportant at the time. It was a small, cracked clay tablet, no larger than a paperback book. Unlike the other tablets, this one carried no carvings of deities or elaborate symbols of royal power. There were no illustrations or decorative flourishes at all. Instead, its surface was covered with rows of wedge-shaped marks known as cuneiform. These markings were clearly numbers and symbols arranged in neat lines, but to the naked eye, they appeared dull and meaningless. The man who discovered this tablet was Edgar Banks, a well-known archaeologist and adventurer. Banks had a reputation for risk-taking. He traveled through dangerous territories, bargained with local tribal leaders, and often smuggled valuable finds across borders to sell to collectors. His adventurous life, combined with his love of archaeology and treasure hunting, would later lead many to believe he inspired the creation of the fictional character Indiana Jones. For Banks, this particular tablet was nothing special. It looked ordinary compared to the magnificent statues and ornate carvings being unearthed at the same site. He packed it up along with other artifacts and eventually sold it to George Arthur Plimpton, a wealthy collector fascinated by rare manuscripts and ancient knowledge. Plimpton later donated the tablet to Columbia University in New York City. There, it was carefully labeled, cataloged, and placed in storage with thousands of other ancient relics. As part of the cataloging process, the tablet was given the name Plimpton 322, Plimpton for the collector who donated it, and 322 as its catalog number in the university's collection. Since it had no images of gods or kings and appeared to contain nothing more than simple numbers, scholars paid it little attention. At the time, experts preferred to study tablets with clear cultural or religious meaning. This one seemed too plain, too practical, and not worth further investigation. For years, the tablet sat unnoticed, a silent relic among thousands of others. Eventually, a few scholars began to take a closer look. The more they studied it, the clearer it became that something about this tablet was unusual. The arrangement of its numbers hinted at a hidden meaning that no one could fully explain. What no one could have imagined was that this small, unremarkable piece of clay would one day reveal a secret powerful enough to shake the foundations of history. Centuries after it was first created, and decades after it was unearthed, a completely different kind of mind, artificial intelligence, would finally decode its strange markings. The discovery would expose a secret number that proved the Babylonians had mastered advanced mathematics more than 1,000 years before Pythagoras himself. But before the world could grasp just how groundbreaking this was, scholars first had to understand what they were looking at. And that journey began with the first careful study of the numbers themselves. The numbers no one could explain. When researchers finally examined the tablet closely, they realized it was unlike anything they had ever seen. Most ancient Mesopotamian tablets carried stories of kings, hymns to gods, or records of trade. They usually included clear markers such as dates, temple names, or tallies of goods. This one was completely different. It had no words or symbols tied to rituals or commerce. Instead, its surface was covered in neat, orderly rows of numbers. There were 4 vertical columns and 15 horizontal rows, each carefully etched with figures in the Babylonian cuneiform style. It did not read like a story. It looked like a chart, a table of information built with purpose. Scholars assumed it was some form of record-keeping. Ancient societies relied heavily on written records for agriculture, trade, and taxation. The challenge was that these numbers did not behave like anything familiar. They didn't rise and fall in the natural patterns of food storage, tax payments, or temple offerings. There were no labels to indicate what was being counted. There were no weights, no measurements, no names, and no dates. The numbers were too precise, too deliberate. They followed a hidden rule, almost as if they were part of a calculation rather than a list of real-world items. Historians began putting forward theories. Some argued it could be a catalog of gifts given to a temple. Others suggested it tracked trade shipments or taxes. A few thought it might be a builder's reference guide, possibly used for laying out walls or marking boundaries. These theories seemed logical at first, but none of them survived closer examination. When scholars compared the figures across all 15 rows, the same repeating patterns appeared. These patterns didn't match anything in the known world of Mesopotamian administration or religion. It was as though the tablet was speaking a language no one could quite understand. Then came a breakthrough. In the 1940s, a historian noticed something that left him stunned. Certain sets of numbers on the tablet matched the exact relationship found in right-angled triangles. Today we call this the Pythagorean theorem, which says that the square of a triangle's longest side equals the sum of the squares of the other two sides. This realization was shocking because it suggested that the Babylonians understood a principle of geometry that wouldn't be formally documented until Pythagoras, more than 1,000 years later. The discovery split the academic world. Some researchers were thrilled, seeing it as proof that ancient Mesopotamia was far more advanced than anyone had imagined. Others were outraged, calling it an overreach or a wild coincidence. Heated debates broke out at conferences and in academic journals. Many dismissed the idea, arguing that the pattern was accidental and meaningless. As the years passed, the excitement faded. Without clear proof that the numbers on the tablet truly represented advanced geometry or predated Greek discoveries, the bold claims began to lose support. The tablet slipped into a strange place between fascination and doubt. It was remembered as an intriguing artifact, but no one could say for certain what it really meant. Scholars understood that something remarkable was hidden in its markings, but with the limited tools and knowledge of their time, they simply could not uncover the full truth. The broken puzzle, missing pieces, missing truths. For years, the strange tablet sat quietly in museum archives, occasionally studied but never fully understood. Most researchers had moved on, focusing on artifacts that seemed more promising. But according to reports, a small group of archaeologists and historians became fascinated by it. They were convinced there was something hidden in the arrangement of the numbers, something no one had been able to see before. Their curiosity drove them to gather more experts, and soon mathematicians and linguists joined the effort, each bringing a different skill set to the investigation. As they examined the tablet under special lighting and magnification, a troubling detail became clear. While the tablet appeared mostly intact at first glance, many of its inscriptions were badly worn. Some of the wedge-shaped marks had faded so much that they were nearly invisible to the naked eye. Hairline cracks ran across the surface, and small chips had broken away over time, erasing portions of the numbers. In certain sections, entire lines were incomplete, as though they had crumbled slowly over the centuries. The tablet was not destroyed, but it was far from whole. Key parts of its message were missing, leaving gaps that made the full pattern almost impossible to see. This discovery changed the direction of their work. Without the missing numbers, no theory could be proven. A single absent figure might completely alter the meaning of an entire row. Earlier interpretations, they realized, had been built on assumptions rather than facts. It was like trying to solve a puzzle with half the pieces missing. The scholars knew they needed to go beyond simple study. They needed to rebuild what had been lost. According to unverified reports, the group began by carefully documenting every visible mark on the tablet. They used magnifying lenses, tracing paper, and later, high-resolution photography to capture even the faintest scratches. In some cases, they worked under angled light to make worn symbols stand out through their shadows. These images were then sketched by hand and traced onto graph paper so that the layout of the tablet could be reconstructed with as much precision as possible. With these detailed reproductions in hand, they compared the surviving numbers to other known Babylonian tablets from the same era. Some of these tablets had complete rows and columns, giving the researchers potential clues about how certain number sequences might have continued. They even traveled to other museum archives, hoping to find tablets that had been misfiled or mislabeled, possibly holding pieces of the puzzle without anyone realizing it. The process was painfully slow. A single number took days or even weeks to decide on. For example, if a damaged section contained part of a wedge-shaped mark, some scholars argued it represented the number 6, while others believed it was part of a 9. That tiny difference could change the entire interpretation of a row. In one case, they reconstructed a missing figure only to realize that it disrupted the logical flow of 2 other columns, forcing them to start over. Some guesses fit neatly, aligning perfectly with the surrounding numbers and strengthening certain theories. But others threw the entire table into chaos. A misplaced figure could cause impossible results, like a triangle that didn't balance mathematically, or a sequence that broke the repeating pattern entirely. Every wrong assumption created new contradictions, leading to heated debates within the group. Despite their determination, most of their work ended in frustration. The gaps were simply too wide, and the surviving data too fragmented. Traditional tools like rulers, light tables, and manual calculations could only take them so far. Even after years of effort, their reconstructions remained incomplete, filled with tentative notes and question marks. Still, the attempt was not a complete failure. It confirmed one crucial fact. If they could reconstruct the missing numbers, they might uncover whether this artifact was simply a tool for basic calculations or evidence of advanced knowledge far older than anyone believed. To understand how shocking that possibility truly was, they needed to look back at the civilization credited with creating much of our mathematical foundation, the ancient Greeks. The Greeks were supposed to be first. For centuries, the ancient Greeks have been credited with laying the foundation of geometry and trigonometry. Their work was not only theoretical, but also deeply practical, influencing nearly every aspect of life in the ancient world. Pythagoras, one of the most famous Greek mathematicians, is taught in schools worldwide as the first person to identify the special relationship between the sides of a right-angled triangle, a principle we now call the Pythagorean theorem. This discovery allowed people to calculate distances with accuracy, which was essential for everything from land surveying to building stable structures. Greek mathematics went far beyond simple triangles. Euclid, often referred to as the father of geometry, compiled knowledge into a set of 13 books known as the Elements. These texts laid out the rules of geometry in a systematic way, creating the logical framework that is still taught today. Euclid's work helped architects design complex buildings and engineers plan large-scale projects with precision. The Greeks also introduced trigonometry, the study of angles and their relationships. Hipparchus, sometimes called the first true astronomer, created the earliest known trigonometric table. This tool allowed ancient scientists to predict the movement of the stars and planets. Navigation at sea became far more reliable thanks to these calculations, helping sailors travel across the Mediterranean and beyond with greater confidence. These discoveries shaped fields like architecture, astronomy, navigation, and engineering. Greek builders used mathematical principles to construct iconic structures such as the Parthenon in Athens, carefully balancing symmetry and proportion. Astronomers like Ptolemy relied on trigonometry to map the heavens, laying the groundwork for future generations of scientists, including Copernicus and Galileo. Even the process of dividing farmland and organizing cities was influenced by Greek mathematical thinking. Around 500 BCE, Pythagoras and his followers were seen as pioneers who unlocked the secrets of triangles and angles. Their methods transformed abstract ideas into practical tools that could solve real-world problems. This is why, for centuries, history books credited Greece as the birthplace of advanced mathematics and the starting point of modern scientific thought. Everything we know today about measuring distances, charting the skies, and constructing cities traces its roots back to ideas developed during this remarkable period. But the strange Babylonian tablet presented a troubling possibility. If the numbers carved into its surface really described right-angled triangles, it would mean that this understanding existed long before the time of Pythagoras. At this point, the team knew traditional research methods had reached their limit. That was when a new kind of investigator emerged, one that was not human. The rise of artificial intelligence offered a way to analyze the tablet in ways no scholar ever could. At this moment, one man, Daniel Mansfield, decided to take the leap. With AI as his tool, he set out to finally reveal the truth hidden in those ancient numbers. AI reconstructs the past. In recent years, Daniel Mansfield, a mathematician at the University of New South Wales in Australia, stumbled upon an image of the tablet while preparing teaching materials. According to reports, Mansfield had a fascination with ancient mathematics, and something about the strange, orderly numbers caught his attention immediately. While others had dismissed the tablet as incomplete, he saw it as a challenge. He believed that modern technology could succeed where traditional methods had failed. Mansfield understood that humans alone could not solve this problem. Researchers had been studying the same fragment for decades without finding answers. What was needed was a tool capable of analyzing enormous amounts of data and detecting patterns far too subtle for the human eye. This was where artificial intelligence came in. Unlike earlier scholars, Mansfield had access to advanced machine learning software designed to process ancient writing and numbers at incredible speed. Mansfield assembled a small team of mathematicians and technology experts. Their first step was to create extremely high-resolution digital scans of the tablet. These scans captured every detail, from deep cracks to the faintest scratches left behind by the original scribe. Once digitized, the images were fed into AI software trained to read cuneiform, the writing system used by the Babylonians. To give the AI context, the team provided it with data from thousands of other Babylonian tablets that were fully intact. These tablets served as a reference library. By comparing patterns, the AI learned how Babylonian numbers were usually arranged and how they related to one another. This allowed it to make highly accurate predictions about the missing sections of Plimpton 322. The process was slow and meticulous. The AI would generate possible reconstructions, and then the team would verify its accuracy before feeding the results back into the system for further refinement. Slowly, the blank spaces began to disappear. Columns that had been damaged beyond recognition were filled in with numbers that perfectly matched the surviving portions. It was like watching an ancient puzzle rebuild itself after thousands of years. At first, the team believed they were simply restoring a lost record. Everything seemed straightforward, as though they were reconstructing a simple accounting table. But then, something extraordinary happened. As more of the numbers emerged, the team noticed patterns that went beyond basic record keeping. The figures were too precise, too deliberate. It was as if the tablet had been created according to a complex set of rules that no one had ever seen before. According to Mansfield, there was a moment when the entire team fell silent. The AI was not just filling in missing blanks. It was revealing a hidden structure, a design so advanced that it challenged everything historians thought they knew about ancient mathematics. What had once been a broken artifact was now coming alive on their screens, piece by piece, until it became clear that they were uncovering something far greater than they had imagined. With the reconstruction nearly complete, Mansfield and his team prepared to take the next step. They needed to test the meaning of these numbers. What they were about to discover would not only solve a puzzle that had lasted for 4,000 years, but also force the world to reconsider the very origins of mathematics itself. The secret number emerges. As the AI processed the tablet's data, Mansfield and his team watched closely. According to reports, the AI began to highlight a pattern that no human researcher had ever seen before. The numbers were not random. They were connected, every single one of them fitting into a carefully designed system. At the very center of this system was a single key ratio. Mansfield later described this ratio as a master key, because once understood, it unlocked the meaning of the entire tablet. When applied correctly, every number suddenly fell into place, revealing the complete structure hidden within the clay. What had once looked like scattered figures now became a perfectly balanced table with clear relationships between each value. To understand why this was extraordinary, consider modern trigonometry, which most people encounter in school. In today's system, we use angles and decimals to solve problems involving triangles. This approach is effective, but it has a limitation. Decimals are approximate. Every time a number is rounded, even slightly, it introduces a small error. In simple calculations, this error is tiny. But when multiple steps are involved, those small errors can add up. Over time, especially in construction or astronomy, these inaccuracies can lead to serious problems unless corrected with advanced tools like calculators and computers. The Babylonians solved this issue in a completely different way. Instead of working with angles, they focused entirely on side lengths. Using their base 60 number system, they created exact ratios between the sides of right-angled triangles. For example, rather than saying a triangle had a 30-degree angle, they would describe the exact proportional relationship between its three sides. This removed the need for decimals and rounding entirely. Their calculations were exact from the very start, with no margin for error. Imagine a modern city surveyor trying to map out a perfectly straight road over a long distance. Even with digital equipment, there is always a tiny margin of error. Mansfield's research showed that the Babylonians, with nothing but clay tablets and styluses, were achieving precision that could rival or even surpass what we get today without computer correction. Their method was so advanced that when run through modern software, it produced results nearly identical to those made by high-end technology. The implications were astonishing. With this kind of accuracy, Babylonian builders could have planned large-scale projects like temple foundations, palace complexes, or massive irrigation canals with unmatched precision. They would not have needed to rely on repeated trial and error or rough measurements. Instead, they could calculate exact dimensions beforehand, ensuring that walls met at perfect right angles and that water flowed smoothly through canals without overflow or blockage. This system showed a deep understanding of geometry long before the tools we take for granted existed. It was not only proof that the Babylonians understood the principles of right-angled triangles, but also evidence that they had developed a practical, highly sophisticated mathematical framework. This was more than a clever trick. It was a window into the mind of an ancient civilization, whose knowledge was far ahead of its time. The implications were staggering. If the Babylonians truly used this system, it meant they were capable of building with incredible precision. Historians now believe this knowledge could have been applied to real-world projects. For example, it could have allowed ancient engineers to perfectly align massive temple walls or design irrigation canals with flawless measurements. Instead of relying on trial and error, they may have been using exact mathematical relationships to guide construction. This was more than just an academic discovery. For centuries, the Greek mathematician Pythagoras had been credited with identifying the relationship between the sides of a right-angled triangle. That relationship is taught today as the Pythagorean theorem. But now, the numbers on this tablet prove that the Babylonians had mastered the same concept more than 1,000 years before Pythagoras was even born. This revelation completely overturned the traditional timeline of mathematics. It suggested that the roots of advanced geometry did not begin with Greece, as history books have long taught, but in the ancient cities of Mesopotamia. Even more shocking, it hinted that the Babylonian system was, in some ways, superior to the one we use today. This one tablet rewrote history and proved the Babylonians were far more advanced than we ever imagined. But if just a single artifact could overturn everything we thought we knew about the origins of mathematics, what else is still out there, buried beneath the sands or locked away in museum drawers, waiting to be decoded? Could there be knowledge that might completely change our understanding of the ancient world? Share your thoughts in the comments. What do you think might still be hidden, waiting to be discovered? Thanks for watching. See you in the next one.